So much of Unit 1 is basically just an introduction to topics that will be built on throughout this entire course. Ecosystems and how they function and how we're changing the organization is a recurring concept. The biogeochemical cycles come back when we go into water issues, air pollution, and climate change. Biodiversity and our impacts on it also carries all the way over to the last unit. So it's okay if you don't fully understand all of these concepts your first time seeing them. They're going to come back, we will revisit these topics, and you will grow and build in your understanding. Trust the learning process. So let's clarify what I think is important to keep in mind as we develop these concepts. Climate refers to both the precipitation and temperature patterns of an area throughout the year. And when describing anything related to climate, it's important to consider both how temperature changes month to month and how precipitation changes month to month. One last thing I want you to keep in mind here is in the southern hemisphere, the seasons are flipped. When it's winter in the northern hemisphere, it's summer in the southern hemisphere. So let's take a look at these two climatograms, right? They look totally different, but they're both of a temperate deciduous forest ecosystem. The seasons happen in different months, sure, but it's hot in the summer months and cold in the winter. The rain follows the same pattern. It occurs seasonally. I've never seen a time in which this is a question on the AP Environmental Science exam, but I definitely see it coming at some point, so I would carefully read any climate-based questions so you know whether the context of an ecosystem is in the northern hemisphere or the southern hemisphere. The biggest misconception I see in food webs and trophic pyramids is when the 10% rule is applicable and when it's not. 10% rule refers to the energy transfer between trophic levels in an entire ecosystem. Food webs only show the transfer of energy between specific organisms, which very rarely is exactly 10%. You know how some people can eat all day and never gain any weight, and then there's people like me who can smell a cupcake and instantly gain 5 pounds? There's just too many variables involved in individual feeding relationships to precisely model energy flow between individuals. But when you compile everything in an ecosystem, all the producers, all the primary consumers, all the secondary consumers, the energy flow between these trophic levels converges at a value much closer to 10%. So the 10% rule applies to ecosystem-wide models like the trophic pyramid, not so much to food webs where you're looking at interactions between individual organisms. Chemistry is tough. It's essentially its own language that you have to learn how to speak and all the vocabulary and grammar involved with it. Now, while this isn't specifically a chemistry class, you do need to know some basic chemistry to understand what we're discussing. In a chemical reaction, your reactants, the left side of the equation, react to produce the products, the right side of the equation. Photosynthesis, for example, carbon dioxide and water react to produce glucose and oxygen gas. And the whole point of knowing chemistry is understanding how to track those carbon atoms. The carbon in the CO2 is the carbon that ends up in the glucose after photosynthesis has occurred. That glucose is then used to build carbohydrates. So now the carbon is in a carbohydrate molecule. Then the plant gets eaten by a cow and digested. The carbon, after a whole bunch of different chemical processes inside the cow's guts and metabolism, they end up becoming the carbon inside fatty acids, which is how animals store our energy. After respiration, the carbon that was inside the food we ate ends up being the carbon in carbon dioxide when we exhale, and there's carbon going back into the atmosphere. And that's really what we're looking at when we're talking about biogeochemical cycles. We're tracking the movement of carbon, which molecule is part of, and for how long. Same for the nitrogen cycle, where we track nitrogen, and the phosphorus cycle, where we track phosphorus. It's important to be specific with terms. Plants don't absorb carbon out of the atmosphere. This is pure carbon, or at least the graphite inside of the pencil lead. This is a compound composed almost completely of carbon atoms. And this is not what plants absorb during photosynthesis. Plants absorb carbon dioxide. So, when discussing cycles like the nitrogen cycle, carbon, and phosphorus cycle, where the element we're talking about can be part of different molecules in different reservoirs, it's important to be specific about which molecule you're referencing in your examples. Does it? Yeah, magic. Woohoo. Really, it's the water cycle that's the weird one because water doesn't really undergo any chemical changes, right? Ice is H2O, water vapor is H2O, but water does change physical states as it exists in different states of matter. But I do want to bring up the issue of evaporation. Heat is not what causes water to evaporate when we're talking about the water cycle, right? Water evaporates at 100 degrees Celsius, which in freedom units is 212 degrees Fahrenheit. After it rains, we see the water does evaporate, but where on the planet does it reach 212 degrees Fahrenheit? Light energy is responsible for most of our surface water evaporating. Water evaporates at non-boiling temperatures because the molecules at the top of the liquid have less intermolecular attraction than those within like the rest of the bulk of the water. Remember, those are the hydrogen bonds you learned about in chemistry class that result from water's dipole moment because it's a polar molecule. They literally kind of hold on to each other because one side is kind of positive and one side is kind of negative. When the top layer of water is exposed to sunlight, some molecules gain enough kinetic energy from the photons to escape into the atmosphere. That's it for the major misconceptions from Unit 1. Please keep these in mind as we move into future units, as all these topics do come back up again. But for now, go explore the outside.